Hello, everyone, and thank you so much for joining us today for the 2020 Hackaday Prize Dream Team final presentation with our Conservation X Labs team. We're so excited to see how they've progressed since their initial concept review just a couple of months ago. My name is Magenta Strongheart, and I'm Head of Design and Partnerships at SupplyFrame's Design Lab. And for those of you who don't know, for this year, for the Hackaday Prize, we've done something totally new with the Dream Team initiative, where we've essentially recruited top engineering talent from around the world to tackle some of our nonprofit partners' most difficult challenges. So today we're going to be hearing from the Conservation X Labs Dream Team about what they've developed for our nonprofit partner. I'd like to first give a huge thank you to our sponsors of the Hackaday Prize this year. Without them, none of this would be possible, and we really appreciate their continued support for the open source hardware development, especially in regards to the Dream Team initiative this year. So thank you to SupplyFrame, DigiKey, Microchip, and ARM. We really appreciate their contributions. And again, this progress would not be possible without them. Without further ado, I'm going to pass it off to Giovanni Salinas, our product development engineer, to tell you more about today's challenge that we're addressing and our dream team that is here on the call today.
Thank you, Magenta. Hello, everyone. And I want to start by thanking our Conservation X Lab panelist, Sam Kelly, product engineer and conservation technology program manager. Thank you so much for being here today, Sam. So we're here today for the final presentation of the Conservation X Dream Team Challenge. This team includes Aaron, Toby, and Leonardo. Hello, team. And thank you for being here too, and thank you for your dedication. So we've set this for the previous teams. Designing a product in the middle of a pandemic, being so far apart from each other, requires a special level of commitment and talent. We have Canada, Nigeria, and Venezuela. It almost seems too random. Seems like we picked the locations with a raffle, but we didn't. It was all about you. It was about your interviews, your passion, and your commitment. So your team is basically about that. Creative, it's inventive, and a lot of applied hard skills. I have to say that you didn't have a lot of time for iterations. This challenge in particular is very complex. So you had to get it right at the first try. And after a lot of research, after a lot of electronics, math, software, and robotics, you came up with an awesome concept. So honestly, you guys are professionals. So thank you again for your dedication and your talent. And I'm very excited to pass the microphone to the team. So the floor is yours, Conservation X Dream Team.
Thank you so much. My name is Oluwatobi. We're really excited. I have my teammates. We've been working together as friends for over 2 months now, and we see each other almost every day. So we are Team Heja. Next slide, please. So Heja is just a name coined from a Yoruba language in Nigeria, meaning fish. That's the translation. So we feel like let's just pronounce it like in a phonetic way, calling it Heja. So for us, we are in a mission, and our mission is to develop, a cheap and very affordable, low-cost ropeless chair. And part of the mission is that how can this be available globally? Imagine a fisherman in Africa can afford this ropeless chair, like so cheap, and everyone all over the world also can afford it. So part of the research we were able to do while working on this project is we realized that, there are different ghost chairs that were, ropes from traps that are just thrown out there without anyone tracking it or, kind of identify where they are. And part of the challenge there is that how can they track all these traps? How can they look at where they are? How can they potentially, fix them whenever they are bad? These are the kind of challenges that are out there. And we felt like we are Heja. How can we solve this in a very short time? How can we develop a solution that is more affordable, that is accessible, that is also location-based, whereby people can just sit somewhere and with their gateway or their device, they could just access the buoy and they could just track wherever the buoy is. And that's part of our design or focus when we're working on this project. So, but part of our research, we thought that there are still potentials that we couldn't achieve during this stage. And this, it's about, we want to gather data about the buoy. You want to be able to network the buoy, whereby imagine you have 1,000 buoy and you just sit somewhere and you can control the buoy. I mean, using LoRa technology, which is part of one of the things that we felt like it would be so important we had. And of course, part of the discussion we discussed is having like a camera, whereby underwater camera that we can still implement with the buoy, where we can see what is happening with the buoy underwater. But I mean, these are future possibilities that we intend to add. Next slide, please. So our design, we try to narrow it down and say, we want to focus on a specific thing. And one of the things is we want to help fishermen in order to be more data driven. We've discussed this over time. Anytime we're talking, we talk about it almost every day, that how can fishermen be data driven? How can they work with data and to know where their buoy is and make the buoy more intelligent? And then part of it is how can we reduce the loss of chair in the water, and how can we locate it anytime we're using our intelligent buoy? And part of the design is we're talking about the low cost. How can this be as cheap as $250? So we also focus on the battery management system, thinking about lithium ion that could be powered for at least 72 hours. And then think about it, me, I'm just seated somewhere in Nigeria and I have access to the circuits with the design, and I can just locally build edger. And that's the kind of capability we want to be able to have all over the world. We want to be able to make it like anyone where you are, because it's open source, just go to our platform, copy the information, use it. You can reference us and say, you got this from Edger, and you can replicate it at a very low cost. That's part of our focus for this design. And I'm going to pass you to Erin, she's going to take us through the mechanical process of the design. Erin.
All right, thanks so much, Toby. So now in this section, we're going to be talking about the mechanical design and what we did in order to reach a fully tested prototype concept that we made. So the ropeless gear system of AJET is comprised of 3 subsystems. Those are the onboard gateway, the intelligent buoy, and the release mechanism. And we made prototypes for all 3 of these. So first, the onboard gateway. This one was pretty simple. It's just an enclosure. And it's able to enclose the circuit board for the onboard gateway. And with a bracket, we can also make it fit the buoy A board, which has cellular connectivity. And Leo will talk about that a bit later. Next up is the intelligent buoy. So the intelligent buoy is some 3D printed pieces along with the circuit board, a servo motor, and an internal magnet wiper. And this all fits into an enclosure, which we used was a Nalgene water bottle. We decided to go with this approach because the Nalgene water bottle is translucent, so that way we could eventually use a camera to be able to see through it. The way it works is that this entire assembly, it attaches to the inside of the lid, and it can go into the enclosure. Then we have the wiper with the magnets to attach to something on the outside of the enclosure. That brings us to the release mechanism. The release mechanism is where the intelligent buoy is housed underwater, and then it can be released. So when the buoy moves its internal magnet wiper, the external magnet wiper follows, and then that means that the buoy is no longer constrained, so that way it lifts to the surface of the water. Additionally, there's a rope spool for the rope to unwind when the buoy is making its journey up to the surface. And all of this is mounted onto a base of HDPE, that was CNC'd at the design lab. There's some 3D printed attachments and brackets to mount everything, such as a camera mount and the ballast weight. For the ballast weight, we used a 10-pound dumbbell. Here's what the release mechanism looks from the top and underneath where you can see the ballast. So that's all great and to see the computer models, but like, what about real life? Well, we made a prototype, and this is it on the shores of Lake Ontario in Canada. And this is just after it finished a test. So let's take a look at what the test looks like and how it operates. All right, so what you just saw in that video is that entire process of the buoy being released and then rising to the surface of the water. And that worked multiple times. So what was the road to get there? How did we even reach that? Well, what we did was we created some iterations and tested various hypotheses along the way. So this was during our first test. We even were testing illumination, so that's a 3-watt LED underwater. LEDs in water can be used for bycatch reduction sometimes. What was interesting though, and this is really good data for us to collect, was seeing that the lights illuminate all of the suspended matter in water. So this is something to keep in mind for when we do intend to use computer vision, that there will be some particles clouding it. Then after that test, made some improvements to the next iteration and testing that out, throwing it into the water. The water was moving at a higher speed, so it was interesting to see how cloudy it can get. And what we were really testing is the external wiper, because at that point it was sort of difficult to see, like, is this working at all? Is this going to be a possible solution for transferring movement from the inside to the outside? It wasn't working then because the battery was in the way of the movement. But once we solved that issue, we saw some really great results. And luckily on this day, the water was pretty intense with high waves, well, high waves for Lake Ontario. So here you can see the buoy, it's moving its internal wiper, it's slamming into the ground. That day we were also testing some simple ballasts of containers filled with sand. And then we also tried to rock. The rock didn't work, but it was all right because we knew we were going to make the release mechanism anyway. And we verified that the magnet wiper worked. So here it is again, because it's just so cool to see it working. It moves and then the buoy lifts up. This was based off of time. So every 2 minutes, the servo would actuate, and there was enough time to reset it then. And it looks kind of random from the outside when you see something appear from the bottom of the water out of nowhere. Then this curious thing happened when we were testing. So there was water that leaked into the enclosure. As you can see here, this was not noticed when we were testing. So that's just the water moving around. But the good news is that because the way the buoy was mounted, it meant that a lot of water would be needed to sort of fill it up before it starts to do damage. Here you can see the aftermath. There's more water. But interestingly enough, after drawing everything out, everything was still functional. Even when testing, the only thing that stopped working was the servo. So it was a little interesting insight as to, I guess, either really good luck or maybe it's just the way the pieces were aligned. So yeah, that was good news. It still worked. It was a really interesting thing. So more to be continued in further testing. A little bit more information about the intelligent buoy. So it uses a Nalgene enclosure, which is polycarbonate. So the depth is actually limited pretty much by the strength of the lid. And we have some ideas on how to improve that. Actually, at the design lab, they printed some of our new lid designs that can screw onto the top out of Formlabs resin. So it's possible it could be made much more in much more durable materials than what it is currently. So ideally, we're looking at depths of about 150 meters for the official brand, or off-brand if we were to scale it, perhaps, then about 30 meters, which would be fine for shallow fishing applications or if the buoy just needs to be at the surface. Of course, further testing to verify would be necessary. So future work would be to do some user testing, getting this into the hands of fishers so that way we could hear the feedback from their perspective. On the intelligent buoy, doing some more lid experimentation and improvements and testing if there's camera distortion and how well the view works. For the ropeless system, it's just a few minor improvements such as improving how the buoy gets loaded in and locked into place with the external magnet wiper, then distributing the ballast weight and stronger magnets. From there, we could start to look at benchmarking so that way we could see where our solution compares to others. Here are the links where you can see all of the information. And with that, I'll pass it on to Leo for talking about the electronics.
I will start talking about the electronics, what we developed, what tests did we made, and what is the documentation available. We specifically put a lot of effort in having as much documentation as possible, because the idea is that we want the product to be functional, to be a good platform for continuous development, to create even more research, or it can be adaptable for like a very specific product. So always the documentation is very much appreciated. Next one, please. Now, we'll briefly discuss a little bit about the concept. We're starting with the concept and which one are the most important elements that we took into consideration. We have the intelligent buoy, the onboard gateway, and in this case, in the middle, the components of the onboard gateway, and on the right, we have a phone as a means of visualization, a tool for visualization. So over here, from left to right, the most important components for the intelligent buoy are the ESP32 that is used as the microcontroller, the LoRa that is used for communication to the onboard gateway, and the GPS. Those are the most important components. But now, since from the beginning, we were very focused, we wanted a design that could adapt to different types of motors. Even so, at the beginning, we were very sure that we wanted to use servo motors, but we weren't sure if at some point of the design we would like to change that. So that's why we added an additional motor driver that expands the possibility of the design to add DC motors or stepper motors if it suits the design. The onboard gateway, the most important components are LoRa to communicate with intelligent buoy, and the SP32 that anything that uses Wi-Fi to transmit the information to the phone that can be used locally to read the information. The onboard gateway is a device that the fishers carry with themselves. Next one, please. Now, we already discussed the most important components, but there are a lot more components that are going to be that I'm going to be bringing. In this one, we also wanted to add to the design a GSM GPRS model. On top of the models that I recently mentioned, there is GSM GPRS specifically for G. And we, using these components for the Buoy, we designed two printed circuit boards, Buoy A and Buoy B. Why two printed circuit boards? The original has all of those components, the 5 of them that we have in the left. But the size that was higher than the limitations that we had for our design. So we wanted to experiment and to have that design and to test it. But also we had a very specific limitation for the design that we were building. So we designed Buoy B. Buoy B, the difference between Buoy A and Buoy B is that Buoy B doesn't have the additional GSM GPRS module that was added sort of like a backup. So if you cannot establish like the normal LoRa communication, then the Buoy can emit information using 4G. So that's why we have Buoy A and Buoy B. Another thing that we can look at the PCBs is that we wanted to be have the PCB with a higher adaptability, easy to solder, and we also, for example, look at the connector uses like terminal blocks or very high and very big and rough connectors that allows to make quick changes, even for a prototype, but also to be easy in the field that we're working. Next one. Now for the onboard gateway, we have a similar situation, and here we also have an addition. On top of the elements that we discussed, for the onboard gateway, we saw the opportunity to add an additional battery charger. For this one, we only have 2 components, and we added to the design a Li-poly battery charger that can be easily adapted, so it's easier for that device that the feature, so that the developers, that the product can be carried with themselves, can be easily plugged into a micro USB, and you can charge the battery easily. Next one, please. Okay, during the planification stage, we recently talked about the onboard gateway and how it has a battery charger. This is the Buoy. And for all of the designs we designed and we created wiring diagrams. In those diagrams, we take into account all of the other components that are not directly soldered to the PCB, but they are also important parts of the design. And in this case, for example, in the Buoy, we can see that we approach using a LiPo battery that is a higher voltage than 5 volts, that is connected to a buck converter that reduces the voltage specifically for 5 volts, and then connects to the Buoy. And in this case, we have 2 images because we have Buoy A and Buoy B. We have diagrams for both of them. Something that I talked before that I'm briefly going to mention, we also consider for the wiring diagrams the adaptability for different types of boards. Here we can easily visualize how the same board can be connected to different types of motors, from left to right, servo motor, DC motor, and stepper motor. Now, this is a very important part that we try not to overlook. That is that I mentioned, it was the documentation. We also, when considering the cost of the prototype, the bill of materials, the list of all of the components, we also, as a part of the documentation, we have the assembly of all the board and different steps of which you can follow to solder them. Of course, we now we have numbers for the most important components. The 5 of them haven't changed, but these assembly guides can be very useful for moving forward the design and using it later for people to be like to diminish the time that they have to spend to implement what we made. Now, for the proof of concept, and this is for the testing, specifically the test for the electronics. Briefly mentioning, we have from left to right, we have the Buoy on the left, and the middle onboard gateway. On the right, we have the phone. And the board on the left and in the middle, they communicate using LoRa. And the board in the middle communicates to the phone using Wi-Fi. But also there's an additional thing that since we have an ESP32 as a microcontroller, we use it because we selected because the higher amount of documentation, but also for the test, it's easier to test even on to have information from the board, even of the field, because we created asynchronous web servers, asynchronous servers in the ESP32. So as a part of the testing, you can connect using your phone to the board in the Onboard Gateway as normally intended to be to work, but also you can connect to the board that uses the Buoy. And you can also look like internal messages and look information. So they are also prepared for debugging, but not only debugging in the laboratory, but also debugging on the field. That's what's very important. For future improvements, there are small details in the PCB. While we were working with them, we found out that there were small mistakes. There wasn't one that completely ruined the design that made it impossible to use. But there are, since we created like the footprints, there are different screw holes that need to be fixed. There are text indications in the PCB that also need to be fixed. And in the overall, for making a prototype with a lower price, it's also recommended to if you want to really lower the price of the design, you can remove the breakout boards and use the inner components of them and add it to the principal printed circuit board. So, and of course, remove if we add additional components, that those can be removed to like reduce the size and reduce the price. Now I'll leave you with my with our team member Toby.
Thank you so much, Leo. I'm going to talk about briefly, like it's so like fast about the software design. Can you go to the next slide, please, Erin? So thank you, Leo, for explaining that. This is my own Azure board, you know, and we have to all solder it independently. It's the same like the picture you saw on what Leo posted. So we decided to pick Arduino platform because we want to work more collaboratively. It's a platform that is at least generally available that people can work with and play with because of the libraries. We've got libraries for LoRa, for GPS, and all sorts of things. So it makes our work faster. So why the choice of LoRa? Leo explained briefly about that as well. Is that we want the fast, long distance connectivity whereby we can access data easily. And one funny thing happened when we tried to select GPRS. In Canada, they're about to phase out 2G, but in Nigeria, they're not going to phase it out yet, maybe in the next 20 years, we don't know yet. But then we now say, okay, let's just move a little bit further and prefer to use 3G and 4G, because with that, even if they phase it out in Canada, it's still going to work in Canada. So, and going forward, the SIM card choice, we selected hologram, thanks to Giovanni for shipping it out to us. So that hologram makes us not being specific that, okay, I'm going to use Vodafone for my configuration. In Nigeria, I'm going to use MTN. So hologram is just a platform that all of us can use the same network, and all the data that are being pushed, we know that it's reaching the data points that we've all created. So for the motor driver, so Leo has created different interface like servo motor, DC motor, but more specifically, we decided to use the driver, which is the TB6 that is on the slide, in order for us to test for the prototype. So pretty much like that talks about the software part and the design. I will hand you over to Erin, which concludes the presentation for today. Thank you so much.
All right. So when we start to dream and really start to see these buoys be deployed, the question is raised of, will this scale? So for the electronics side, Leo prepared this bill of materials that shows the price for 1,000 units. What we can see here is that we would likely have to create our own circuit board in order to bring the cost down as low as possible. On the mechanical side, we would have to fine-tune the design so that way it's for manufacturing on CNC machines or the little pieces through injection molding. Right now, there's a lot of time used on 3D printing, and that could be better applied to faster machines and with better materials too. Interestingly enough, a quick search on Alibaba for off-brand Nalgene containers reveals that for 1,000 units, they cost less than $1. So that's still a viable enclosure for us to use that is still transparent. So that's a little glimpse into the future for potential scalability. And with that, I'd love to thank Hackaday and Conservation X Labs on behalf of Team Asia. Thanks so much for all of your effort and help in this as well, especially Giovanni for the numerous video calls over the course of the design sprint and sharing your knowledge too. It's been great, and we can't wait to hear the feedback from Conservation X Labs as well about how it could be possible to test this even further. So yeah, thanks so much.
Awesome. Congratulations, Conservation X Labs Dream Team. Thank you so much for the wonderful presentation and really diving into all the different parts that made this successful. And it was really awesome to start out with the video of the buoy making it to the surface. Very exciting moment for you guys, I know, and for all of us who've been following along your journey. So congratulations, and excited to hear what Sam thinks about the progress.
Yeah, honestly, this blew me away. This is fantastic. I'm so impressed that you guys managed to do this across three different continents, and you know, in such a short amount of time, especially given what's going on in the world right now. Honestly, this is more than I could have ever hoped for. So, firstly, just congratulations. It's really fantastic. I jotted down a few questions as we were going through, and honestly, you guys got a lot further than I would expect people could do in 2 months. So I'm really excited about the possibility of taking this further. And I guess that would be my first question is given maybe a little bit more time and maybe a little more funding, what would be the next steps for you to get to that next stage? You talked about scalability, but what would be the next steps for each of you?
I can start, and then we'll go through for each of us. So the next steps for me is to improve the design of the buoy a little bit, just so that way it's more secure, especially with the lid, as well as the release mechanism. So what you saw was like the HDPE piece itself is sort of like Swiss cheese. It has a lot of pockets and holes. Those are filled with huge 3D printed pieces. So now that we know where everything is supposed to go, we can eliminate that and just do the drill holes. So that would help a lot. And the time involved in that design and testing it would be the next steps.
In the case of the electronics, I will briefly mention, for example, one of the things that can be done, the project still needs more time to test the electronics on the field. We made a lot of tests individually, so we test the mechanics specifically for the specific part of the design that controls the motor, so we can really check that the mechanism works. So one of the in the case of the testing, one of the next steps would be the proof of concept, but not the bare bones components working together. For example, with myself having the electronics working and having the mechanics will be an integration of them. Another thing is that for the electronics, the price of the onboard gateway of the electronics specifically, the onboard gateway, the price is about $84, and for the buoy, the price is about $130 approximately. So one of the things is that choosing now that once we finish the test, if we manage to make more tests, we can reduce the cost. We can make a new model. Since this one is great as a prototype, and it's great for experimentation, but also has additional things, has redundancy, has different connections for everything. So that's great as a prototype, as an investigation tool, but not as great as a product. So easily it can lower the price. I won't say how much, but for example, for the motor that is like $20 or $15, it can be removed if the motor that we're using right now works. So that's $15 less. And if the GSM board is not necessary because LoRa works very good, also it can be removed. Another thing is that we need also for the testing, it's very important to test like the localization of the antennas and how they need to be oriented to really be sure that it's going to have the coverage that we are expecting from. So as a summary, I would say like more testing, and the benefit for the testing, it can be lowering the price of.
Yeah, in addition to that, I agree with Leo. So another point is about having most of the components in a miniaturized way. Imagine if we are still going to use a modem, we don't have to use a modem module. We can just get the chip, and then we also get each of the ESP chip and just make it much smaller. With that, the space for the buoy will be more compact. So, and selection for ESP is quite cool, but then what about if we can research more and see which other microcontroller we can use that is cool, that is even more cheaper, that could still provide the same exact, processing power. And, I think there are a lot of them in the market. So, but because of time, we couldn't really deep down. So if we have more time, we would definitely check out some other processing power that we can use that is as well cheap and provide the Wi-Fi capability as well. So, and that's that. And another point is some other functionalities that we've discussed before in our meeting. It's about having, some kind of messaging platform for fishermen, whereby it gives them quick messaging conversation which shows them where their buoy is, which also required internet access, of course, through the GPRS that we've discussed. Meaning, imagine you have your WhatsApp and you just type buoy A, or let's say buoy 1 or buoy 2 or buoy 3, and it will return back a message to you on WhatsApp and say, hey, this is where your buoy is with the lat and log. With that, it's just fun to have around. So that's another thing that we've discussed, that if we have more time, we want to just explore and see how it goes. Thank you.
Yeah, I mean, so it sounds like everyone's really focused on reducing the cost. I mean, I'm really impressed that this already costs less than $250. I know that it is a major barrier for the existing like lineless or ropeless fishing solutions in the market. So what I really also love about what you guys have done is really think about how we could deploy this in a number of different countries around the world. And so I just wanted maybe just to quickly understand that a little bit more, whether that was the focus, whether you were looking at, ways that you could perhaps allow people to build their own devices wherever they are in the world, or whether this is something that you're thinking, let's reduce the cost, let's try get these units out, as cheaply as possible. I'm just wondering how you're balancing those kind of competing factors.
That's actually a question I was going to ask you after this.
Okay,
which
good.
is interesting. Was like and if anyone, Aaron, Leo, or Toby had a response you wanted to say to that, feel free, to interrupt. But I was curious, as in regards to Conservation X Labs goals and sort of programming mission and that sort of thing, do you think you guys would be more interested in getting 1,000, 10,000 mass-produced units that you would be able to manage the distribution of and sort of the adapting, the adaptation of, or do you guys look to more, finding partners, offering a solution, getting stakeholders in, on location or whatnot, like local stakeholders to take on what they think is the best fit for their area?
Yeah, it's a complicated question. I think that it really depends on the fishery. Now, I think that this type of solution is sorely needed in many small-scale fisheries, and that really relies on community connections. And I think that the distributed manufacturing approach of allowing local people, local businesses to perhaps build something like this in country or on site would be really useful. But in some more, let's say I don't know, for example, in America, it would make maybe sense. I see this is a huge demand in America, for example, is what I'm most familiar with, to be honest. And it's having a mass-produced product would also be beneficial. So I would say it really depends on where it's being implemented, and not to say that either of those approaches is wrong. I think that it would really just honestly take some more customer discovery and understanding what people want. We really try not to bias our decisions or processes too much until we hear from customers. So I don't think either way would be disqualifying. One of the things that may be a problem is reliability, and quality control and quality assurance, if it was made by a number of different people. Just because, if this breaks, one of the, I guess, the downfalls of this design is if it breaks, that it's lost, right? So reliability is going to be key with this. And so however we do this, and I'm really excited about this design, actually, I think it's a really interesting way of tackling this problem. However we do this, we'll have to really make sure the reliability is very high. So yeah. Now, does anyone else have any thoughts on that? Yeah.
Can I say something real quick? I think Team Asia, please correct me if I'm wrong. I think the focus on price goes back to your initial research when, well, you asked local fisheries, what would the barrier be for this? And I remember, as in many things in life, price would be a barrier, right? So the cheaper and more affordable it is, especially in underserved communities, the easier it would be to be adopted, right?
Yeah, 100%, 100%. Yes, it's cheaper, but also I think one thing we've really found is the ability to hack and fix and service is really important. If we have to replace something, if it breaks and it's not fixable, I think that is a major problem. So that's kind of why I see both ways working.
I was just going to say, I think it's really interesting. This conversation has come up with some of our other dream teams as well, and there's some nice, I think, opportunities, sort of overlap and maybe potential for future, collaboration as well. When, for example, with the UCPLA team, the discussion of reproducing the assistive devices that were developed over the last couple months, we talked about, again, the pros and cons of sort of taking advantage of distributed manufacturing and local makers and innovators, and our network, of course, within the open source hardware community versus mass production and the advantages for their specific product, but also our other dream team nonprofit partner, Field Ready, is all about like the work they do is distributed manufacturing for crisis relief and sort of crisis aid situations, and their dream team challenge was distributed remote sort of quality control, and how do you do that for those kinds of products. So there may be even more tie into for all these different strategies on how to address the longevity and reliability for these things. But I appreciate that this is a big question. I think because of so many of the advantages of distributed manufacturing, and we've seen, especially recently with the PPE, production across the world through the distributed manufacturing sort of strategy, the potential for that to really make an impact. So just wanted to chime that in.
Yeah, I would like to add something to the question that Sam asked us, specifically the beginning. We prepared the project as to be a great platform that can be achieve the goal, but also we select a specific component like the ESP32, like the modules for motors and LoRa. They're very well documented and very, very popular, so it's very easy to find documentation and to find similar products. So this is a platform that can be go in very different directions, depending on where do you want to take it. If it's like a developer or a research team, for them, it's like very important, like having lots and lots of documentation, because they will normally want to take it and change everything and add stuff and add different things. For that, we thought about it. For example, we have specific connectors to include more modules and connect them to the board. So the board is thought as that you can make it, and then you want to think, oh, I want to add an LCD, I want to add another thing, and you can connect it. So it's malleable for that, and that makes it great for researchers, for people who want them, because you're building on top of development boards that are very popular and very used. And of course, if you look at it as a product, then you have a different point of view. Then maybe you would like something more like specifically suited just for the task that you're doing, and you don't want a $30 development board if you can buy a $2 microcontroller that can do specifically the same thing. So the thing about this is that we focus on making it work and having a lot of documentation available. So if you want to make it more specific, you can take it, you can replace the components, knowing that they can work together and then that they can work in the specific way that we're proposing. And if you want to use it more like a research laboratory, then you can make them like it is and connect more information. But I think the idea is that the prototype we wanted to be as good as to be easy to take in the direction that you want to take it. Of course, we thought about principally using it as a product, and for that we wanted to work and to have a proof of concept. So that's what we had in mind, like the proof of concept, because that's important for the product.
Yeah, I think that's awesome, and I think that choosing, for example, Arduino really helps with that kind of thing as well. There are a number of different boards that are used around the world, for example, that may not be ESP32, but it could be another board that's to that specific region. But that portability across platforms is really interesting. Along those lines, I'm curious. Regarding actually the mechanical side of things. Now, you're using the Nalgene bottle, which I think is like genius. I think it's a fantastic use of something like that. But I was just wanted to understand a little bit more about that mechanism. How are you? I mean, one of the big problems in working in the oceans is dealing with water everywhere around electronics. And I was just wondering if you could perhaps dive into, making that reliable, making sure we didn't perhaps lose electronics to water ingress. If there was any sealing or mechanisms you'd explored to help make sure this bottle can get to, for example, 30 meters underwater.
Yeah, it's a great point. Luckily, all of the electronics are just in this. So the release mechanism itself, there we go. Luckily, all the electronics are just in the buoy. So the release mechanism itself is just pieces put together. So for the buoy, it's mainly just all about the lid threads. So something that was recommended that we haven't tried yet is putting tape on the threads, special tape. And then that would probably secure it and probably stop the problem altogether. Other things that were...
And just quickly on that, to service that, are you removing the lid each time, or is it possible to, for example, charge through there to prevent that, like any perhaps degradation perhaps of the thread over time or anything like that? Is that something that we could think about, or I'm just curious, just generally?
We could think about inductive charging. The wall thickness is 2 millimeters. So I don't know if Toby can do that in his head right now, if that works. But anyway, yeah, it's likely possible. And yeah, each time it has to be serviced, then it just is removed. Something else we were exploring, especially for buoy A, was cutting the Nalgene. So that way we still keep the polycarbonate aspect, which is strong. And then here is where we would then 3D print a cap onto it that way the Buoy A board, which is longer, would be able to fit, and we would do a double O-ring seal. We haven't gotten that far yet.
That's awesome. Yeah, I really like the use of the analogy, and I've also seen PVC pipes be used as well, and they have their drawbacks in that often there's like defects because they're not always used for high pressure scenarios. You can get those pipes, but they tend to be a little more expensive. So, I mean, it's a really interesting use of materials. I also do have another question around the release mechanism. Now, it's currently done just off a timer.
Yep.
Perfect. And that's just how would someone program that, for example? Is that done through the app? What is that kind of user experience like?
Well, for me, the user experience was typing in a long into the code, but I'm sure Leo has some further thoughts on what the future user interface could be.
Yeah, we specifically have a counter for the release mechanism. It can be, we can have an independent counter. We have a real-time clock as a part of the GPS. So we have a little redundancy there. But the thing is how you can how can you input the specific amount of time that you want the device to wait until the buoy is released. That is easily made by communicating directly with the buoy, or you can communicate to the onboard gateway. And before deployment, when you are preparing everything, you can connect via the phone, via your phone. So you enter your phone and access directly the device, and you can set the time. So it's not necessary to specifically reprogram the devices just to fix a new timer. And another thing is that we also, this is a benefit of using the ESP32. It has over-the-air programming. For over-the-air programming, that means that you can, yes, that was one thing that we had in mind when we selected it. So the development board is expensive, but it has its benefits, and that's one of them. So we figure out if we, for the mechanical design that at that point wasn't perfectly fixed and very completely designed. So we thought if it is programmed over the air, then if we have to make changes for the design, we don't have to keep opening and closing it just to change a timer or a specific information in the board. So you have those ideas. You can change the firmware over the air, or you can communicate through the onboard gateway and through the web page.
That's awesome. Yeah, understanding that kind of how the user interacts with is kind of interesting for me, because I think that's going to be the pain points that the fishers kind of end up with, and you know, how are they going to get their gear back? How do we communicate that? How do we, you know, put that in with heavy gloves, for example, if it's in a cold area, or, you know, in salt water, those kind of things. So interesting. I also do want to ask fail safes. Now this design specifically, the reason it gets to be so compact compared to a lot of the other solutions out there is because you are, you know, having an actuator under the water that releases the bottle. Now, if that fails, you don't get your gear back, correct?
Right now, yes.
Okay.
But what?
Yeah. Is it, what kind of redundancies, if any, had you thought of?
Yeah, one idea would be to have a sort of a spring attached to the external wiper, and that spring would rot over time. So that way, eventually, even if the electronics die inside of the buoy, or sorry, if the electronics break inside of the buoy, over time would just spring would, and then the external wiper would move away, and then the buoy unleashed. That's
a smart idea, because I think some way that doesn't rely on the core electronics to function at all would be, I think, fantastic. Because yeah, it would prevent a lot of the nose scare that could be an unintended consequence if the device doesn't function 100% of the time. Yeah, and just finally, I'm really curious about how you're going to move forward with user testing. I think it's really important to get some feedback from users, and so we'll put out by you just to see if there were people that were willing to help with that. What would the beta testing look like?
So in Canada, they have a bit of a process already for like testing ropeless gear, which is kind of cool. The first step is to do a test in freshwater. So in Lake Ontario, you don't need any permits or anything to go out and test it. So that would probably be a bit further along, but the first step essentially like doing a really deep water test with it. Then after that, you can apply for a permit to test it in salt water. And that's the ideal location, like on the East Coast, the Maritimes, testing it there. And at that point, we would ideally test it with a fisher. So what we did at the very start of the project was make connections with people in the Department of Fisheries and Oceans here in Canada. And they'd be able to connect us with some fishers to do the real test with that we would need a permit for. As well, apparently there are these ropeless gear competitions where they bring together all the competitors and we see how long it takes for each gear to reach the surface. So I guess participating in that competition would be a good idea too.
That's pretty cool. I just wanted to add something. There's another team, the UCPLA team, that they also designed a device with electronics. And the question was raised, of course, how would we scale? I think it's an interesting roadmap for them that could be applied here. Since that device is going to be used by people with cerebral palsy, we are going to be scaling step by step. So we have a prototype right now that they're going to be made 5, and we're going to get feedback from the users. And after that, we're jumping to 20 or 30. And then we are going to get a broader range of interaction in terms of limbs, dexterity, et cetera. And then that's when we are going to take a decision. Are we confident? Are we happy with this to jump straight to mass production? Or should we go with an even larger test group? So this, I think it would be interesting for Asia team to put it with numbers. Locations is good, but numbers would probably help make it clearer in terms of why don't we make first 10 units and then those can be tested somewhere, then 30, et cetera, et cetera.
Thank you so much for doing this. This is such an important problem. This problem ghost gear is not only hugely degrading to the ecosystems where people fish around the world, but it's also a major source of ocean plastic. Conservation Excellence is running a prize in the not too distant future on ocean plastics, and people don't realize how much of this ghost gear contributes to that problem as well. Now, this solution, I think, goes a long way to helping people, not only in countries that have the industrial fishing capabilities, but also those with large community and artisanal scale fisheries as well. So I'm really excited about this. I think that there's a lot of legs to this project. I would really love to see this happen. And so any way that Conservation X-Labs can support you all, let us know. I'm really excited to continue this relationship.
Thank you, Sam. I think that's an excellent note to end on. I know I can speak on behalf of Design Lab Hackaday and Supply Frame and say that we're so proud of how far this team has come and this solution. And I think it was definitely one of the more dynamic and challenging briefs that was put forth by our nonprofit partners. And I think even in early discussions and figuring out how to narrow things down and what was the appropriate challenge, we had a lot of thoughts of how this would go. So it was really excited to just see you guys latch on with this kind of energy and make something happen, and start with your research and really bring it all the way to a viable prototype. And we're really committed to continuing the collaboration and partnership with you all and with Conservation X Labs, and to see, how far we can push this down the pathway to getting it into the hands of the users. So thank you all for your incredible, work and dedication and the presentation today. And thank you, Sam, for your time throughout the last few months in supporting the Dream Team and working with us on this initiative. Thank you all. And I will just say, for our audience, if you're interested in learning more about this whole process that the Conservation X Labs Dream Team went through and want to stay up to date on their progress, definitely check out their Hackaday IO page. You can search Conservation X Labs Dream Team on Hackaday to see all of their amazing documentation that they sort of hinted at on this presentation. And be sure to check in with Hackaday, Design Lab, and Supply Frame on all of our socials, Instagram, Twitter, and YouTube and Facebook, to keep updated on our last presentation with Cal Earth, and of course, any upcoming updates for the Hackaday Prize and future initiatives. Thank you all again for your time today. Super excited to see where this goes.